Hello guys, welcome back. So here we have another question on communication systems from GATE EC 2024. A wide Gaussian noise W of t with zero mean and power spectral density n naught by 2 when applied to a first order RC low pass filter produces an output n of t. At a particular time t equal to tk, the variance of the random variable n of tk is dash. So before attempting to solve this, we need to understand many terms. So first we will start with wide Gaussian noise. So we all know noise is a random process. So if it was deterministic, we can write it as a function of something. For example, f of t equal to sine t or sine t plus something. So we can write it in the functional form and we know at each value of time instant what will be its value. But for noise, it is a random process. So to describe how it will behave, we need to go to the probability distribution. So it doesn't say exactly how much amplitude will it have at that particular time instant, but it gives a probability that this much amplitude will have this much probability of occurring, something like that. So this probability distribution is what is meant by this Gaussian. So Gaussian has something like this. So this is the Gaussian probability density function. And what it says, so for values close to 0, it has a higher probability of occurring than values far from 0. So this is the first thing, which is the Gaussian. What do you mean by white now? So white noise. So we already talked about the probability distribution function. But now if we come to the frequency response or the frequency distribution of the noise, which we can also call as the power spectral density. So white means that it is actually constant throughout the entire range of frequencies. And this is what is given by n naught by 2. So why do we call it white? Because let's say from sunlight, there is white light coming, right? And if you pass it through a prism, it just splits into different wavelengths and we have different colors from violet to red, right? Similarly, here also it has all the frequencies. So here the different wavelengths are nothing but different frequencies, right? So here also we have all the frequencies. That is why it is called as white noise. So throughout the entire range of the frequencies, it is constant and its power spectral density is equal to n naught by 2. So next what they are saying, so this is W of t and it is applied to a first order RC low pass filter to produce an output n of t. So we are taking this W of t, which is a wide Gaussian noise, we are applying it to a first order RC filter, which means that it has 1 R and 1 C, right? And we are getting n of t. So what is the frequency response of this network? So h of f is nothing but, it is a first order. So it is 1 by 1 plus 2 pi f RC, right? And in terms of power spectral density, we have to just take the modulus. Here you will also have j component, right? So once you take the modulus, it is 1 by 1 plus 2 pi frc whole square. So W of t is having this power spectral density. And how will this h of f look? So if you see, it tapers out like this, right? Somewhere around 1 by 2 pi rc. Here also minus 1 by 2 pi rc, it tapers out. So this is the initial input power spectral density. And once it passes through this, what will be your output? So output will be this into your input, right? So n of f mod square or the PFT of this is n naught by 2 divided by 1 plus 2 pi frc whole square. So how will this look like? This will look exactly same, only it will scale by a factor of n naught by 2. So this is our output power spectral density. But what they are asking, at a particular time t equal to tk, the variance of the random variable n of tk is dash. So now we have the power spectral density. How do we arrive at the variance? First, what is the variance? Noise is a random variable, right? So what is the variance of a random variable? So if noise n of t has some distribution, let's say given by this x, then what is your variance? Sigma square is expectation of x square minus expectation of x whole square, right? So now from this mean, it is given that it has zero mean. So if W of t has zero mean, then n of t also should have zero mean. Because this system is only filtering your frequency response. Still your Gaussian distribution is intact. It is not going to change your Gaussian distribution. So it is still zero mean. So this one is equal to 0. So your sigma square is nothing but expectation of x square. And your x square is nothing but, it is a distribution of n of t. So it is, since n of t is continuous, this we can also write it as, this is a random variable, right? So I'll take it from minus infinity to infinity, n square of t, this is square, into dt. So why this is possible is because noise is a ergodic process. So here if you see, I have gone from a random variable to a time variable. So why is this possible is because noise is a ergodic process. So what does ergodic process mean? So suppose I have a noise. So let's say this is my noise, okay, with respect to time. Now I want to see the noise at some time t equal to tk, okay. So I'll take this as tk and we want to find the distribution of this n of t at t equal to tk. So one way to do it is I will take some n1 of t, n2 of t. I'll just keep repeating this, okay. So each time of course I'll get a different value, different waveform, right? So let's say I repeat it some 1000 times or some n naught times, okay. So each time I'll get a different value. Now with this value I can try to find my probability of each of these value and try to plot the distribution. And if you see, we already saw that for this case it is going to be Gaussian. So what does ergodic mean is, instead of taking all this different points for different experiments, if I just do one experiment and I take all the points of the noise and put it as a distribution. So instead of taking points at each tk, I will take one waveform and plot all these amplitude as a distribution. So what ergodic says is both are going to be same, okay. So these both are equivalent or same. So noise has that special property. So that is why expectation of x square is going to be expectation of this distribution x. But here this is n of t is distribution. So these both are equal only because noise is a ergodic process. So we got that. So now we arrived at sigma square is equal to integral minus infinity to infinity n square of t dt. But now we only have our power spectral density. How do we arrive here? Right? So if you see, your power spectral density is nothing but n of f into n conjugate of f. So now if you come to the time domain, if you take a inverse Fourier transform, multiplication in frequency domain will be convolution in time domain. N of f, what it will be? It is n of t. And n conjugate of f, if you remember, your n of f is nothing but integral minus infinity to infinity n of t e power minus j 2 pi f t dt. So n conjugate of f is nothing but integral minus infinity to infinity n conjugate of t e power j 2 pi f t. And noise is anyway real, right? So this is n of t only. So now if I have to go take this to minus j pi 2 pi f t t, what should be this? I need to do a transformation of t to minus t. Then this will become e power minus j 2 pi f t dt. So the inverse Fourier transform of n conjugate of f is n of minus t. So this you have to remember. And this is nothing but your autocorrelation function r of tau. So if I have to write it out, r of tau is nothing but integral minus infinity to infinity n of t n of t plus tau into dt. So if I just substitute tau equal to 0, I'll get this sigma square, right? Variance. So r of 0 is nothing but your variance. And r of 0 in terms of your n of f whole square is nothing but, so for that r of tau is nothing but your inverse Fourier transform of this function, right? So it is minus infinity to infinity mod n of f whole square e power j 2 pi f t dt. Sorry, df. So r of 0 is just your average of your power spectral density. So this is average of power spectral density. Actually not average, it is the integral, right? Integral of PST. So you have to remember next time while solving that your variance is nothing but integral of your power spectral density. So now can we integrate it? What we have n of f, this one, right? N naught by 2 by 1 plus 2 pi frc whole square. So n naught by 2 I can take out, it is constant. 1 by 1 plus 2 pi frc into df. This is whole square. And I can do a change of variable from f to alpha. So 2 pi frc equal to alpha. So if I do that, sigma square 2 is equal to n naught by 2. And d alpha will be 1 by, sorry, df will be d alpha by 2 pi rc. So 1 by 2 pi rc integral minus infinity to infinity d alpha by 1 plus alpha square. So integral of 1 plus alpha square is nothing but tan inverse of alpha. And tan inverse of alpha from minus infinity to infinity is infinity minus tan inverse of minus infinity. So this is nothing but pi by 2 minus of minus pi by 2. So this is equal to pi. So we have n naught by 2 into 1 by 2 pi rc into pi. So this is equal to n naught by 4 rc. So sigma square is n naught by 4 rc. This is your answer. But few important points to remember is that when the power spectral density is n naught by 2 and it has a cutoff at 1 by rc, right? The 3 dB bandwidth is 1 by rc. or 1 by 2 pi RC with respect to F, then what is your sigma square or the integral of your power spectral density? It is going to be equal to n naught by 4 RC. So this one you have to remember. Other thing which we already said you should remember is your sigma square is nothing but your integral of power spectral density. So this is the actual derivation, but it is just important for you to remember this so that you don't have to derive it every time. Okay, so anyway, this question answer is n naught by 4 RC.